Welcome student in our virtual classroom. Today I will discuss the slider crank mechanism. It is the 25th lecture of engineering mechanics. Here I will discuss the two-dimensional planar motion, and slider crank mechanism belongs to two-dimensional planar motion. Today only the velocity part that I will discuss, and in the next class I will discuss the acceleration part of the same mechanism. So let's start with different numerical solution.
This is a problem of slider crank mechanism. This mechanism is observed in piston cylinder arrangement of an engine. You know, an engine means a combination of piston and cylinder, and the piston is reciprocating within the engine. In a very roughly we can show that the piston cylinder arrangement is like this. This is the cylinder, it is the piston. Now within the piston, while combustion in the running process, this piston is moving within the cylinder in a reciprocating way, to and fro motion. Finally our wheel is rotating in circular motion, and this circular source of the this circular motion is the piston. So we need to convert this reciprocating motion to circular motion, and that is done by this type of mechanism where the piston and the wheel that is connected by linked by these two link AB and BC. This link AB is called crank, and this particular link BD is known as connecting rod. Now see, when it is reciprocating and this point A is fixed, and the crank AB only can rotate about point A, but there is no net displacement of point A. Then by this mechanism, when the piston is reciprocating, it will rotate. Now here in our problem, the length of these two link AB and BD is given, and the angular velocity of this crank is also given. It is 2000 rpm per minute, revolution per minute. We have to find out the angular velocity of the connecting rod. You see, this crank AB is only rotating. The point D or the piston is only linear translation motion is there, but the connecting rod BD, it is subjected to the combination of these two motion. At one end reciprocating, other end rotation, and finally it is subjected to planar motion or general planar motion. Now, like all other problem solution, first we will note down what given data is there in terms of the notation. NAB for the AB link, RPM is 2000. The length of the link or length of the link is 75, and for this link it is 200 millimeter. So from this data we can calculate the angular velocity omega, and we know angular velocity equals to 2 pi n, and hence it is 209.4 radian per second. Now using law of sine, what is the law of sine? That for any triangle, the side length by opposite angle ratio is same. So if we consider here the triangle ABD, for this length and this length is known, and opposite to this side the angle is beta, and opposite to BD side angle is this 40 degree. Here we don't know the angle, consider it is beta. Now use the sine law. So what is the sine law? The sine 40 divided by the opposite side length means 200. Again sine beta by opposite length AB means 75. So from these equation we can get the value of beta, and that is obtained here 13.955 degree. Now we can draw a velocity diagram at different points of the mechanism. The velocities are Vv. Vv is the tangential velocity. As AB is rotating, absolute rotation only, rotation about fixed axis, so the end point B, the velocity is tangential to the radius vector. For this rotation of AB, the radius vector is AB. So the velocity, their direction is tangential to that. Whereas for the end D, as it is only reciprocating, now when it is rotating in clockwise direction, then definitely D will move right, and when it is anti-clockwise rotation or next part of this movement, it will go backward. So this is the V direction. So now we know the velocity direction of VB and VD, but we don't know what's the relative velocity of the link BD. So for this, it is subject, if we draw a free body diagram separately for this link, then it is like that, omega B, and it is linear motion, translational motion. Then we have to draw the velocity diagram for this link. Before that, find out the VB magnitude. VB equals to omega RB, omega AB, that is 15.71 meter per second. Now for this connecting dot, at this end B, the velocity is VB, absolute velocity of B is VB, absolute velocity of D is VD in this direction. The direction is same as shown in the previous diagrams, VB and VD. And another velocity is there, that is the relative velocity of D with respect to B. This velocity, as it is the velocity of D with respect to B, so it is a function of this radius, and direction is perpendicular to this. You notice when the link AB was clockwise direction, then the connecting rod will rotate in opposite direction, anti-clockwise, and hence this BD direction is upward. Now let's find out the relation VD. VD means the absolute velocity of point D, that can be written as B for this VBD link. Vd equals to Vb plus Vdb, as we already established this equation. Then what's the velocity diagram? Let's draw the velocity diagram here. For this link BD, the velocity diagram BD, rightward direction, VB, it is same as this one, and this velocity diagram is parallel to this one. Now already we have calculated the magnitude of VB, and we know this value of VB, and using the sine law, VD by opposite angle, this is the VD side, opposite angle is this. This is the VDB side, opposite angle is this 50 degree, and for VB opposite angle is 76.05. All the angles are calculated from the simple trigonometry. Now you notice from here VB is known and all the angle is also known. So from this equation we can get the value of VD and VDB, and that is calculated here, 13.09 meter per second, and VDB equals to 12.40 meter per second. And we also can calculate the corresponding angles, means at what angle this angle, at what angle this velocity is working. It is 76.05 with the horizontal as shown in the figure. And as we are getting VDB, we know that VDB equals to omega dB into omega RAB. It is RBD. It is not AB. It is rather dB. When it is dB, then this relation everywhere is dB. For the dB link, omega velocity. For dB link, the radius vector. Means whatever is given the value of BD 200. So substituting the value of RBD and VDB that is calculated, we are getting the angular velocity of dB link, that is 62 radian per second. So this is the answer. In our second problem is similar to the first one, only difference is that here the point A and D, means the piston, is not on same horizontal plane, rather it is placed at elevated height 120 mm from the ground. Now like the first one, all this data is given, means the link length for AB and BD that is given, and for a particular instant of theta we have to find out the value of the angular velocity of the rod BD when theta is 0 and theta is 90. So let's first write down a general equation for this, and before that the given data, NAB given, RAB given, RBD is also given, the length of the vectors are given. Now from the geometry it is very simple that it is theta, then it is the length is 60, so 60 sin theta, and whereas this is 200, so it is 200 cos beta. So the total height is summation of this plus this, so equals to this 120, that is also given here. Now from here this cos beta can be calculated, and hence the value of beta if theta is given. So for theta equals to 0, you substitute sin theta 0, then it is 0, 120 by 200. So beta is the cos inverse 120 by 200. Similarly from 90 also we can calculate the value of theta. Now for this link as omega, and that is RPM is given, we are getting the magnitude of angular velocity. 2 pi n is the formula, and then 16.76 radian per second. Now let's draw the velocity diagram like the first one, as here this motion is anti-clockwise. So VB definitely tangential to the link AB at point B, but the direction is opposite to the problem 1. And here, as it is moving in this anti-clockwise, so this link is relative to this one. Omega BD is rotating clockwise direction, and as usual the point D, that is rotating left, and hence if we assume that the angle here is beta for simplicity of our calculation, and using this equation we can get the value of beta. Now let's draw the velocity diagram. So what velocities are there? VB, VD and VDB. So as usual, VDB is perpendicular to the link DB, and as it is moving anti-clockwise, so DB direction is downward, because when it is moving, link is rotating anti-clockwise, means this end is moving in this direction, whereas this end is moving this direction. So DB is in this direction. Whereas if we write down VBD, means velocity of B with respect to D, then it will be opposite to this and working through this point B. Now from the geometry, as stated here, we can get the value of the we can draw the value of the velocity diagram. VB, this is the direction, same as this one. This angle here, it is 90 minus theta, so this is equals to theta plus beta minus 90 degree, and it is all these angles that is simply calculated from this figure. So for VD, it is horizontal. Now from that velocity diagram, we have to find out, first we have to write down the equation, and before that we know VB equals to, VB means actually VAB. So VAB equals to VB equals to omega AB into RAB, means it is again the formula V equals to omega R, and this is applied, this equation is applied for the link AB, so FDR suffix is AB. But as AB link only absolute rotation is there, so instead of AB we can write down VB also. And this omega AB and RAB, already RAB is given and omega AB is calculated, and substituting this we are getting the velocity 1.0053 meter per second for the crank AB. Now for the end VD, our relation is VB plus VDB, and from the velocity diagram, using the sine law, we can write down these equations. Now we already calculated VB, so similarly like problem 1, using this equation we can have the value of VD and VDB, and the cos beta that is calculated from here, from this equation, for theta equals to 0 and 0, substitute and get beta equals to this. So substitute this beta value and theta value in this equation and get VD value, and that is equals to 0.755 meter per second. And once we are getting VDB, so VDB equals to B equals to omega R applied for the link DB, then we are getting omega dB equals to 6.285 radian per second. And similarly we are calculating the value of the omega when theta equals to 90 degree. And notice that when theta equals to 90 degree, there is no angular velocity is there. The references that I have used to prepare this video is given here.
So this is the discussion of velocity diagram and velocity of slider crank mechanism, which is the two-dimensional motion. And in the next lecture, I will discuss the acceleration of slider crank mechanism. I will request you to follow the subsequent lecture also, and thank you for your patience and listening the lecture. Thank you.